Welcome, everybody. Welcome back, and welcome if you missed the opening session and you're just joining us. I'm Gary Fisher. I'm with the Project Production Institute, and I'm going to be introducing this segment on how do leading companies implement and benefit from production management. So I'm going to lay a little groundwork and then kind of turn it over to others to show you some real good stuff. So as I mentioned in my opening slides, it's going to be a little bit redundant for a few of those of you, but in case you're new, when I was at Chevron, I was looking for validation that our system was performing. It's a system that I helped design. And these were the results. We found that surprisingly only 9% of the industry projects in upstream had met cost, schedule, and attainment. Really poor results. And this isn't unique to Chevron. This is an industry-wide thing. I could use any segment, any set of data. There have been multiple studies done that show that these are typical performance for the construction industry. And as Ed pointed out in his opening remarks, this has been a problem systemic in the construction industry for the last 50 years. We've been flatlined while manufacturing has improved their productivity and their performance by like 500%. So in spite of all our best efforts with the advent of 3D CAD, critical path method scheduling, front-end loading, advanced worker packaging, our production efficiency has been flatlined. So, I always just thought it was knuckleheads that weren't using the system, but I turned out to understand that it was actually the system itself. And I did some really deep dive into the history and the roots of the project practices that we have. And this is what I found. We go all the way back to a guy called Taylor that had a belief that workers are lazy and you needed to separate people from planning from working because the workers would never load themselves up with a lot to do. So you had to have people that planned to work for workers and just hand it to the workers and let them do it. That iron triangle on the right-hand side, I remember my first year as a project engineer starting with Chevron, that it was ground into me. There's a absolute hardwired relationship between scope, schedule, and cost. If you want it to cost less, you got to cut scope. If you want it to go faster, you got to spend more. And then I came to see that these things aren't actually science. They were theories that were put out there. But instead, if you see on the next slide, we built a whole project management system on this basis. And it's very focused on what we do, when we want to have it done, and who we're going to have do it. And that's Chevron's project management system that I helped design was all around doing those three things really well. What, when, and who. But what's missing? It's the how the work will get done. And we were living in this place on the left-hand side, the schedule that should happen. I actually thought the schedule was a plan. I remember telling people, your project execution plan is not complete till you have a schedule that goes with it. And that's all around what you want to happen with dates and progress. But the reality, and this is where project production management lives, is that right-hand side. There's a production system here, and it's going to dictate what's really going to happen. And that's all about project production management. If you go to the next slide, here's what's really going on. Instead of the slide that I showed you on what project management is, we had a product design, which is the scope or whatever it is we're going to build. The process design, which is the techniques, the way we will go about making it. It's the how it gets built. The capacity, those are the people and the resources that are used to build things. The inventory, that's the piles of stuff we have throughout the project that are waiting in queue for something to happen to them. Could be pipe spools ready to be hung. It could be data sheets ready to be checked. And then variability, which are things that don't happen as we expected, which, projects have a lot of. And projects are unrecognized production systems. And that's why not even seeing this, by not even being aware of this on the right-hand side of that equation, we're just missing out. And the way I designed the Chevron project management system, it was determined to fail by these rules. And this is the science that governs project systems. A key relationship is called Little's Law. It's cycle time equals work in process divided by throughput. And think about it. Most sciences have a three variable equation that govern them, like F equals ma, time equals distance divided by speed. And I had a terrible time getting my head around this. How can more work in process actually increased my cycle time, because the system we designed, the systems that we all use, because they're based on the same foundation, generate massive amount of work in process through the project. Because hey, all the work's got to get done, right? So if all the work's got to get done, why get a lot of things going, get them all started. And instead, so by definition, we're causing the projects to fail. We're causing that poor performance. And it's held with it. What really happens on the next slide is that rates drive the dates. The rates at which work are being done actually drive the dates that are generated. And dynamic projects required rapid replanning. Remember that variability that I talked about? Well, that creates the dynamic nature of projects. And if you're not able to rapidly replan, you're going to fall behind, and you're going to go deeper into the hole. And even though we pretend like we have planners that do the planning, the reality is the people doing the work do the real planning. I can't tell you how many times I walked around a job site and said, "Oh, show me your schedule." And they go, "Yeah, that's that pile of stuff over there. That's stuff on the wall that we never look at. Here's what we're really doing." Sound familiar? And then follow the science. So what is this science? Go to the next slide. It's operation science, is the project science. I had no idea that there was a body of science that governed, that described how production systems perform. Now, if you're an industrial engineer, you're going, yeah, everybody knows that. This civil engineer didn't get any training on that, either formally or when I started working for Chevron in the project world. So operation science is the project science. You're going to learn all about that today. And project production management is applied operations science in projects. Now, there are some key relationships that go with that. We're going to try to have a little bit of fun right here and engage you all into what these relationships are. Now, remember, you're the folks that are leading the projects around the world, so we want to kind of test your thinking about your understanding of how these things are related. Cycle time is simply how long it takes to get things done from start to finish. Work in process, or is anything started but not finished? Okay. Throughput is the rate at which work is done, like diameter, inch welds per day, or number of terminations per hour, those kinds of units of the rate of throughput. And utilization is how much of a capacity is used. Think of it as if we got a crane, how much are we using it? 90% of the time, 50% of the time. Even craft productivity is a measure of utilization of the craft. Haul road congestion, or shipping it, you're shipping things from point A to point B, and how much of that shipping capacity are you using? So that's utilization. And the science informs us about the relationship between these key factors and the things that drive any production system. So I want to run this little experiment. We go to the next slide. We're going to take a poll. And so this is kind of new. You'll see this throughout the day. You can either scan the QR code on the right-hand side, or if you go to your chat window, you'll see this link. Should be able to click on it, and then you can take the survey. Okay, so QR code or link in the chat window, take the survey. Let's go to the question. Go to the next slide. We're going to explore the relationship between utilization and cycle time. So utilization is the percent of capacity that's used. Remember that, how much of that crane we're using. And cycle time is how long it takes to get things done. So notice the numbering goes 1 and then 2 below and 3 above, 4 below, 5, 6 below. So put in the number where you think that relationship is, which one best describes that relationship from your point of view. And then we'll see the results when they're ready on the next slide.
I got a request to go back to the barcode. Let me just do that for a second.
Okay.
Some folks might still be working on that. Might take a little while for people to get that.
I understand. This is new to us all here, and
No,
I've been in symposiums where I was fumbling trying to find my camera and say, now how do I do that QR code thing? And took me a while to find it.
yeah, we'll take a minute to do that and then move on down the line. So while we're doing that, when you did this test, did you get it right?
No, no, I didn't. I had no idea what the relationship was. In fact, hopefully I was able to explain what these factors are adequately, but I couldn't even understand what utilization was. It's like, what? And what's throughput and work in process?
Yeah.
All those terms were so foreign to me. Cycle time was the only one of those four that I actually understood. It was kind of intuitive. It was similar to things that we already did, but work in process is such a key term and a key definition in operation science and it took me a while to get my head around that, and what it means and why it's necessary and how it's used and how it can negatively impact a project.
Yeah, it's interesting there. These are fundamental relationships that everybody should understand, like gravity. And then what we'll find, it'd be interesting what we find that if everybody has a common understanding from the answers. So I think we're good on the barcode.
Okay.
So now let people pick.
All right. Pick the one that you think best defines it, or if you have no idea, put in 6.
Right. Yeah, we introduced actually option 6 after doing it for a few times because it was obvious that people are saying, I don't really understand. So that is certainly an option.
Yep. So how are we doing on the results?
Let's have a look.
Nobody's answered the question.
I doubt that. Oh, here we go. Might take a little while.
In the Q&A, Ed saying is the assumption that all the material are there.
Yes. The material's all there.
Thank you.
Good question.
So we're either not getting polls or we're not getting results.
Yeah. Dang it.
Ed, please right click and reload.
Okay. Reload. Oh, there's some action. Whoa.
Oh, okay.
Here we go. There's some results.
Awesome. Well, that's good.
Oh, not many people.
A couple of honest people there don't know.
Right. Let's see. Let's go back to, Eva, if I go back to look at the answers, will that erase this or can I come back to it?
You can come back.
All right. Let's go back and just see. So 3, it's actually kind of what it looks like, Gary. 3, 1, and 2. Yeah, we're the top.
Or 3, 1, and 2.
All right, come on, go back. I had this happen before. I need to stop the share. And give me a second. Let's see if I can. Oh, there's another answer. So we still got a few coming in. I don't know what's going on. It's not. Let me get it. It kind of gets stuck on this slide and it's not responding. Oh, there we go. Okay, so let's go back then. This should work. There we go. What do we say? 3, 2, and 1?
Yeah, interesting. And there's a fair amount for 4. 4 was my answer when I did this for the first time. I thought, hey, man, you get more utilization. You got to shorten the project because, hey, crap productivity. I want people working harder. That's going to take less time of people doing more work, right? Well, let's look at what the correct relationship is based on the science in a couple of slides later here.
All right.
See, it is.
Whoops, went right past it.
Number 3.
There you go.
Utilization increases. There's a turning point there, cycle time will go out. Interesting, huh? For a project person, that was counterintuitive to me completely. And we designed many of our systems to actually increase utilization right up to the max. Or
Well,
think
another
about it
takeaway,
differently. We'd have to pick, how many cranes do you want on site? Well, I don't know. I think it's 2. Well, how do you think? I think it's 3. And we had no science at all to determine how many cranes that we thought we really needed to do the work that we needed. And instead we watched utilization of the cranes. If they looked like they were sitting around, we had too many cranes. If we had all the cranes were busy all the time, then we must not have enough. Let's get another one. All right, let's go to the next relationship. Next slide. We're going to look at the relationship between work in process and cycle time. So same drill as before. You can use the link in your chat or the QR code. And we'll see what you think. Now this thing's humming. That's fun to watch the results come in. Looks like one's the clear leader. So as WIP increases, cycle time goes out. Very good. That's very close. Let's go to the best answer. Actually, you need some WIP, but there becomes a point where it becomes deleterious, and then it starts increasing cycle time. But you do need some WIP in the system. You can't operate with none. Okay, so that's good. So the one thing I want to talk about now is variability. If you remember those 5 levers I showed you, and I talked about variability, it just happens. Lots of stuff happens. I know we assumed it's just the way it is, and we had to have workarounds for all that. Just there's really nothing you could do about it. But of those 5 levers, variability is just really the most insidious. And again, variability is things don't happen the way you expected or planned them to happen. You get surprised, things go haywire. And here's what we do in projects to protect ourselves against variability. We generally, and we could use any kind of part of a project or a whole project, engineer, fabricate, deliver, install. Let's pick fabricate. We give the fabrication team the job to get it done because we ask them to optimize what they do. Well, what do they want sitting in front of them to be able to do fabrication really well? Well, they want all the materials, they want all the drawings, they want everything that they need to be able to fabricate, so they're insulated from any variability coming at them from the upstream side, right? That's what we all do. That's human nature. As a construction manager, I wanted all my materials that I needed for that job sitting in the warehouse, and I drove that project to do that. And I didn't really realize or even think about what are the impacts of that accumulation of material waiting on me to do the construction work, sometimes years in advance. And that means I had to store it, I had to babysit it, I had to maintain it, I had to keep track of it, and somehow it kept getting legs, and people in the refinery would borrow it to use it for something else. I had to replace it. And then some of it it became obsolete through design development or whatever, and we had to replace it. So the true cost of putting all that material and having that available to me so I would never have to wait on material was huge. And even the worst part was I tied up cash. I tied up cash years in advance that could have been used to fund another project and another refinery and generate income. All because I needed to protect what I was going to do with construction. I was only responsible for construction. So there's a direct and a real hidden cost here. And this is huge. And the more that those cylinders become, the bigger they become, the more work in process we have. Remember Little's Law. It means it's going to take more time to do the work, more time to do the work, more cost, more time means lower return on investment. That's what we do. And that's why the systems that we see perform the way they do. They're designed to have substandard performance. So I talked about the PPM framework earlier. I want to revisit that real quickly on the next slide. This is what we're going to be talking about in this segment, is really fleshing this out and looking at people that are actually using it, putting to work their experiences, both in design and in the construction or fabrication. And like I said at the beginning, that this is all based on that gray bullet in the middle. It's all operation science based, dealing with the production system. And the gray ring around that is really the project production framework that you're going to hear about in this session, around designing and optimizing the project production system. This is the what will happen compared to what you'll want to have happen on the schedule, and then controlling that system in a completely different way. It's not project controls, and we're going to talk about that later this morning or tonight, but controlling in a completely different way. So you have design a production system that's operating, and then you have controls in place, and it feeds back into how you optimize that system over time. And that's really a loop that happens to deal with the dynamic nature of projects. So and then once you get that foundation in place, we're going to talk about some of these things later in the day, then you can put to work simulation, artificial intelligence, analytics, IoT, all those things have a solid foundation to work off of and become far more effective. You know, we see often, for example, I saw a great digital application for improving the effectiveness of advanced work packaging planning. Well, so we take something that doesn't work very well and we digitize it to make it work, to make the process work really well, but we're still dealing with a flawed concept. And we got to be careful not to do that. And that's a lot of the kind of improvements that we see around the industry are taking a current practice and making it slick and better, but it's still a current practice. It's still grounded in non-science. So let's hang those things on the real science and get real improvement. So at its core, the next slide, project production management has, well, we dropped a slide there. So back up, please. Project production management has 3 core pieces, and they're going to be discussed this morning, and Ed is going to talk about them in more detail in his remarks at the end of this segment. Designing the project production system, designing the product or facility using computer assisted production engineering or concurrent engineering with the people that are actually going to build it, do the construction, and then control the work and feed that back into the overall system to optimize. Okay, so now I hope you're scratching your head, wondering what the heck is he talking about? What does all this language mean? How does this look like in the project world? And for that, I'm going to hand it off, but I want to reflect on something that we just heard from our neuroscientist, that I need to see it to believe it. Well, that's what we're all about this morning. You're going to see it. You're going to see it on projects, and hopefully we can get you to also then believe it. So I'm going to hand this off to Roberto as a facilitator for our next session.